Good afternoon. Thank you for joining me today. I'm super excited to be here speaking at Data Fest. It's not trivial for me, and I'm all very excited. So bear with me. So again, my name is Ziv. I'm working at Wix, and I'm also a DJ. And we're going to talk about today using AI for music mixing. Imagine a world where we can effortlessly peel apart the layers of music and separate the music composition into its sources, which is the vocals, the beats, and other instruments. Let me show you how a future world of such technology is going to sound like. By the way, everything here is live, so if there's some messed up, just be, thoughtful.
It's your birthday. We gon' party like it's your birthday. We gon' sip Bacardi like it's your birthday. And you know we don't give up. It's not your birthday.
Party on a boy, make a big noise, playing in the street. Gonna be a big man someday. You got mud on your face, you big disgrace, kicking your can all over the place, singing we will rock you. We will rock you. Party on a young man, hot man, shining in the street. Gonna take all the walls one day. You got blood on your face, you big disgrace, waving your banner all over the place. We will rock you. Sing it out. We will rock you.
Jane broke down, G's up, I see exhibit in the cutting name on the trees up. Rough and watch how I move, stick before I play up here. Been hit with a few shots, now I walk with a limp.
Okay, so this is like, thank you. So this is like some taste of how it's going to sound like, and actually how I did that mix, how I blend it all together and make it sound so perfectly, at least to my taste. But it's not that trivial, and this is what I'm going to take you to this aspect of my life today, which is the DJing part of my life. So being a DJ is not only like curate the playlist and move from one song to another. It's also the ability to read the crowd and to select the exact track and to blend it in the exact moment so it will both feel very pleasant to the crowd in the dance floor and also will move the energy in the dance floor from high to low and etc. So the issue is that sometimes I hear something that perfectly match in my headphones and I'm like saying to myself, okay, this is going to be great. I'm now picking what the exact moment and start blending it to the dance floor, but somehow it crashes, okay? And it those kind of moments where you hear as a crowd, you can hear the DJ messed up, and you are like saying, "Oh, I don't understand what he's doing, what he's trying to do." So it happens from time to time. Luckily, we have alcohol in parties, okay? That's really helpful in recovering from such crashes. Let's see how it sounds like. So let's say I pick Adele for a moment. You are all familiar with Adele, right? This song?
There's a fire starting in my heart.
And let's take another song that in my head is perfectly matching each other. Okay, so now I want to try and mix those two together. So I'll skip to this part of Adele where the peak of the track.
The scars of your love remind me of us. They keep me thinking that we almost had it all. The scars of your love, they leave me breathless. I can't help feeling we could have had it all.
Okay, so this doesn't sound quite right, okay? And maybe I can try to fine-tune the sound like those tiny sounds with the equalizer I have in my mixer, but it's not really fit because of different harmony. But again, somehow I did heard it in my head, and it was perfectly matched. So in order to solve that and to be able to actually mix it together, this is what we'll do by the end of this session, is we will learn what sound is. We will talk about how we extract audio features from sound signals and how we can use them in machine learning, and what deep neural networks are bringing to this art. So it all started one day when I got a release note from the DJ software that I'm using. They say something like, "Dear DJs, we are happy to introduce you a unique technology that is going to allow you to actually separate sources of music live in real time into the vocals, the instruments, and beats." And at first I said, okay, it's not really, I mean, I didn't see what the great potential out of it, and I kind of let it go. It was also during like the end of COVID. Still, parties were not really part of my daily routine. And one day, about a year ago, a friend came to me and said, "Hey, I really need your help in creating a karaoke version of a certain track, and it is a very old track." Of course, at first I sent her to, like, okay, try to go to, I don't know, YouTube, or try to find some studio versions of this song, but she couldn't find anything. And then I remember that I have this ability that I can take a track and then separate the sources, because I remember that email. So I pressed a few buttons, and it was magically working. And I sent it over with her track, and it was, she was happy, I was happy as well, but something really triggered me. And as an engineer that I've now played with some unique technology, as an engineer, the next thing I wanted to see is how they do it. So what do I do? A question? That's right, I went to Google. Okay? I actually searched for source separation and neural networks. And I started to read an article and another article and downloaded the data sets and downloaded the code. Everything is online. Everything is on GitHub. All the academic material is just there. And I was playing with it more and more and tried to challenge it even more with hard songs, with a lot of noise, with a lot of instruments, and was trying to challenge the algorithm, and every time it was working. And after a few hours of playing that technology, this is how I looked like. I understood at that point that I discovered something really great, that I missed it for at least a year. And so when dealing with data science problems, we need to model a real-world problem to machines. And so how we model sound, okay? So first, let's understand that sound is eventually air molecules that vibrates in the air, and our ears are sensitive to those tiny vibrations, and this is what our brain perceives as sound. And machines are actually doing something similar. They are measuring the amplitude levels in each time. It's called sampling, and it's happening in constant intervals. So eventually, machines or computers create this visual representation. This is the most common visual representation of sound. It's called waveforms. But actually, waveforms are holding themselves multifactorial information. One of those key factors is the frequency. Okay, if we zoom in, we will be able to see the sine wave, which is the frequency of the sound. We will be able to also gather the intensity of a sound, which is like the local maximum point of an amplitude level in a squared area. And we can also see the timbre, okay? The timbre is like the tone color or the tone quality, but not the quality in terms of like how clear we hear the sound. It's the tone quality of like, let's say if there is a frequency of a C chord, okay, and at the exact same point, a C chord comes from a piano and from a guitar, then the ability to differentiate between those two instruments is the timbre. Another representation other than a waveform, which shows us the amplitude changes over time, is a spectrogram, which is the thing below. A spectrogram is showing us the frequency changes over time. By the way, in order to transform from one way to another, we just run a Fourier transform function over the values of the waveform. But then you can say, okay, where the amplitude levels are gone. So actually, the amplitude levels becomes a variable of the brightness. Okay, so a spectrogram is actually a 3D image of sound. Okay, but for us humans, it's much more convenient to look at 2D images. So as you can see, this is a sample of a C chord, and the frequency of a C chord is 500 hertz. And if you can see, exactly at 500 hertz, just a little bit above the zero, we see like a bright line. So this bright line is the amplitude level. So after we understand that, how we model sound, now we need to know, okay, what we actually model in sound. So when we are talking about pulling out audio features from sound signals, it is very common to think of 3 levels of abstraction. So at the lowest level, we have what we can say like machine and audio engineering kind of values. It's a lot of numerical data. It's not something that we as human can perceive and digest. It is all about values such as the amplitude envelopes, the energy, the frequencies, zero crossing rate. We will talk about some of those later. In the medium level, we have something that is more human perceptual. Okay, we can spot the pitch, and musicians will also spot notes and musical patterns in the sound signal. So this is like the medium level features. And at the highest level, we have what each and every one of us is enjoying listening to music, which is the lyrics, the instruments, the mood and the rhythm and everything that gets us excited. So let's say if I want to for example, if I want to solve the following question, whether this is a car engine, okay, whether a sound signal has a car engine in it, okay? So what I need to do as an engineer, I need to work together with a data scientist to map some features. Let's say we are now experimenting in order to create a data set or train some model. And what we take for this example is the amplitude envelopes, which is like the peaks of the amplitudes, and a little bit before and after those peaks. We get the values from there, and also the zero crossing rate, which is like the angle or the speed when the amplitude levels go from positive value to negative value, and vice versa. So now after I did some training, again, this is just for the sake of the example, okay? Don't like, I mean, you can try it at home, but I don't know if it is really working. So let's say I've trained a model. I now have a model that can say yes or no, whether it is a car engine. I had to actually work on it, to do some trials, to work both engineering and data scientists, and it costs a lot. And deep neural networks actually introduce a whole new techniques to deal with sound and to deal with sound tasks for the sake of machine learning and stuff like that. I mean, it's almost the same revolution for neural networks introduced to images, okay? Because eventually, if you think about it, a spectrogram is eventually an image, okay? So what we do when we use neural networks is we just give the neural network the input, which is the spectrogram, and we expect to get some kind of result, and the neural network will train itself and will extract the feature by herself, and we can just, compare it to some target result that we want to achieve and to calculate some loss function. So actually, we want to do the same when we also want to split the sound into vocals and instrument, okay? And this is pretty revolutionary in terms of the effort that needs to be put on this kind of task, not only on the side of the data science part, like the vendor of such companies that produces those models, but also on the other side of the user. And actually, if I'm taking if I draw some timeline over the history of sound production, so back then, in order to make something, to work with sound and to do something, to manipulate it, I had to buy a very expensive softwares that probably optimized to do a single task, for example, noise reduction, or for example, I don't know, blending, or to do some sound effects. And it was taking overnight some time to run a computer, to run over the night over the sound signal, and to be able to get some result. After that, we did enjoy some of machine learning, mostly in classification area, that came to our help, okay, in terms of classifying stuff, in terms of distinguish certain sounds, but not in terms of source separation, but more like spot some patterns and to try to mix between one pattern to another. And eventually, we are now in this part where, by the way, developing those machine learning models is also something expensive because we need to iterate over and over together with data scientists and engineering efforts. And now we have automatic feature extraction using neural networks, and this is allow us to actually both speed up the training part and also allowing real-time results. Okay, so this is like the real big change. Let's see how this works. We will use Adele as well here. Wait.
The scars of your love remind me of us. They keep me thinking that we almost had it all. The scars of we could have had it all. Floating in the deep. You have my heart and soul.
Okay, you see, it really works in high resolution in real time, as you can spot it, and it does very good work. Okay, it's not only taking Adele's voices, it also takes like the secondary voices of the other singers. I think it is amazing, and let's see how it is actually done. So. Wait, I need to excuse me for a moment. Okay, so let's see how it is actually done. I'm taking this neural net architecture just for the sake of this example. I found it very easy to understand. So first, we take the audio and transform it into spectrogram. Okay, this is the very easy part. It's done very quickly. We have done it years ago. It's not hard at all. And actually, this is like the base of the neural net functionality. It uses both convolutional neural networks that excel in splitting apart all the music parts into very small pieces, and then it uses recurrent neural network to try to build the temporal dependencies between all those pieces. Eventually, and by the way, the convolutional and recurrent part are essential to those kind of tasks of music separation. And in every neural net that does music separation, you will find both these two parts. Eventually, what we get from the neural net is a huge feature maps, okay, feature maps that describes the piece of sound in all of its layers, okay? And we also combine everything together into a mask, okay? And then what I do is like, I'm taking this original input and run the mask over it, and then it works like a filter, okay? So whatever comes out after the masking, is eventually, in this case, the vocals that I can compare to a target result, okay? So in the training phase, I'm comparing until I get like a very small values or values that I can live with in the loss function, and of course, values that I can actually hear it and see that it is working. And if I got the vocals, to get the instruments, it's pretty easy, right? I just need to subtract the vocals from the original value, and then I'm left with the instruments. So this music source separation technology is actually implemented as we speak and revolutionize the entire music industry, okay? First of all, everything related to karaoke. Like they are totally constructing now a whole new music base and everything related to music transcription, okay, because now I can peel apart the vocals and then run a model of transcription, which is also something that was already done. So it's not, it becomes very easy and even more accurate. And of course, everything related to beat matching, DJing, it really helps, and we will demonstrate that in a minute. What I wanted to take from this exact session is that I'm not a data scientist. Many of you probably are, but I'm an engineer and a DJ, and I just read the instructions step by step. Everything is online. I will post it, all the links here, so you can play with it as well. You should actually try and play with it and try to think in terms of creativity, what kind of things you can solve now. Again, it's super fun, and I will post all the links in social media and in the app later. But I want you to know that it is not a rocket science. Like, every one of you can actually enjoy it today. It's very accessible, and it's amazing. So, are you ready for party? Yay! Okay. So we will take the two songs of Adele. We will take two songs of Adele and Butterfly, and I will try to also mix other songs, those two. It's not playing.
I never knew there was a
No, this one.
love like this before.
Okay, so we take this, and we will end with Narcotic, which is a very beautiful song. This one. Okay, so let's see how we can combine everything together. I hope it will be successful. Again, if it's not, bear with me. Sorry.
The scars of your love remind me of us. They keep me thinking that we almost had it all. The scars of your love, they leave me breathless. I can't help feeling we could have had it all this year. Underneath the tears of my heart, you have my heart savage.
Thank you.
There is no need to cry, for a trough is more than this. We can still recall my name, and the month it all began. Will you release me with a kiss? I tried to draw the veil. If I have, I